All right, number 12. 12? Yes. Hold up. Hold up? No. All right, for the built-up structural steel members shown, calculate the moment of inertia with respect to XX and YY centroidal axis. So to get inertia, we have to have the composite neutral axis. That is Y bar and X bar. Do we know one of these? Or is everything? So Y bar we don't know because the Y of this one is here and the Y of this one is here. So we have to find it, right? What about X bar? Yeah, if we're symmetrical, we know where it is. So the YY axis is directly through the center, correct? So we don't really need to locate that. You just need to you would just want to explain where it is, right? It's either such a distance in the geometric center, I'd say. However you want to say it, or you just note it like that, right? So we don't need to do X bar. We know where that is. We do need to do Y bar. That formula is summation of areas and Y's over the total area. So start stacking them up. I'll call the plate area 1. Call the C shape area 2, and there's 2 of them, so we can just multiply by 2 and we do that statement. Area of 1 is 27 times 1. Right? I see it as 1. 27 by 1.
But it's the center.
Oh, this is just the area.
Oh.
Areas,
Oh, I
right?
thought
Like
you were talking
no,
about
no. Now I'm doing Y bar.
the other.
So now we need the Y distance from the bottom, right, all the way up to the centroid of this thing, which is halfway. Right, so that would be Y1. And that's going to be the depth of the C shape, which is 15, and then a ½ inch, 15.5. Yeah, going like that. And then we need area of 2, which is 11.8. And then we need the Y distance to that centroid, which would be 7.5, half of the 15. And all of that over 27 plus 11.8. What do we get for Y bar? Should be shifted up. What?
11.8 plus.
Oh, times 2. Thank you. Times 2 and times 2. So good. We have a number we like.
11.77.
Yeah, it's definitely going to be above the 7.5. It's going to be shifted up. I hear 11.77. Anyone else get that? 11.77 inches. That's important. So that's it's. Huh?
7.60.
Okay. That's this thing. Point 77688.
7.68. 7.
Questions on that? Any questions on that? So we have to be able to do that one first.
15.5 is not one, right?
So yeah, this is A1, Y1. And I called the plate 1.
Okay,
Yep, so we go up 15 and then we go up a half. So 15 and a half.
You multiply it by 2 because there's 2 sections, yeah.
2 C shapes, correct.
Thank you.
And same with down below, right? 2 areas down below. Because we need the total area down there. If there was a hole in something. Hint, hint. You subtract it. You happen to see that in some future test or exam.
What?
What? Huh? What? Maybe on Monday. Yeah,
How many problems? There gonna be 8 problems.
there are gonna be 8 problems. You already wanna talk about the exam. We haven't been through the homework yet. Oh my gosh.
It's gonna be so
And we're
many
doing that on
problems.
Friday. Maybe we should do a mock exam on Friday. Practice exam.
Together, this
Just like a community final.
Yeah.
works so well when we're.
Well, 'cause we're a
Yeah, honestly.
Yeah, we should vote on it, don't you think?
I know we should vote. Yeah, we should.
All right, great. Why don't we just go straight to like the grade that we get? We should vote on that.
I think that's pretty good.
All right,
Everyone has tried hard and.
absolutely.
Yeah.
We
Right.
get an
Effort and.
E for effort.
In democracy or what?
I give you all an E.
Ooh, does that give me the credits?
I don't even know what that is.
E
All right, definitely. This must be the end of the term. Who's bringing pizza is what I want to know.
At 8 AM?
Donuts? Not pizza?
Yeah.
I can eat pizza anytime. I'm just saying. That's a good, that's a good
Someone
breakfast.
brings coffee, someone brings donuts, we can split it. Someone does a joke.
Right?
I'm in.
Extra credit if we bring donuts.
I'm in it. Extra
Oh, wait,
good.
tomorrow's Friday.
Tomorrow is Pie Day.
Friday.
Don't miss Pie Day.
We get extra for
All right.
that.
We're gonna be here all day.
What
What do we do next?
Stuff and things. Do the, transfer.
Yeah, so we have to get the individual inertias first. Then we want to transfer them. Because they're not all in the right location, right? This one's way up here. This one's below the neutral axis, so we need the individual inertias next. So we need I of number 1. That's this plate. How do we get that?
You get the base height,
How do we get the inertia of a plate?
base-
Basically.
Yeah, it's a rectangle, base height cubed over 12. Base height cubed over 12. Because it's a geometric shape, we can just look up. This is a structural steel shape. I already looked that one up, right? But we have to get this one. We have to calculate it. Base is 27. The height is 1, which we will cube. I'll cube that in my head. And then divide by 12. Base height cubed over 12. 27 divided by 12. 2.25. Units. Inches to the 4th. We're good with that? All right. We already know the inertia of the C shape because we can look it up. It's 348 about its centroidal axis. Now we need the transfer distances, D1 and D2. D1 is here. Right, D1. And D2 is, let's put this one down here, it's here. From axis to axis. This is Y bar. Which we calculated 11.76877. So D1 is gonna be what? Y1 minus Y bar. Right, you get that distance between. So Y1 is 11.6 Here, I'll write it out. D1 equals 11.7688. That's y bar to there. And y1 is 15.5. This is negative plus 15.5. What'd you get, Jorge?
3.73.
Some rounding there, maybe. But anyone else get that? Yeah. Okay. And then we need D2. D2 is y bar, which is our 11.76877 minus distance here, right? Which is our half of our C shape, our 7.5. Is that right? What do we get for that? Yep. 4.2687. Everyone okay with those numbers? And now we do what? We transfer, yeah, the transfer formula. So transferring the first one, so maybe some kind of notation saying where I'm going with it, XX, and of the first shape. It's gonna be the inertia of the first shape, 2.25, plus area of the first shape, that's the 27. And then the D distance for the first shape, 3.73, and we square it. AD squared. Inertia about its own shape, area, D squared. Three 380.71. That's what I got.
377.
I got 378. No, 377.
2.25. I'll do it again. 27. 3.7 times plus 377,898. This is rounded probably a little bit, so 377 point, I'll write it 898 inches to the fourth. Really make sure you have units on everything on Monday. Any solution, it's got to have a unit. I don't like taking 1 point because you forgot to put the unit down.
Even if you get it wrong, you get
Don't
1 point
do
for
that.
units.
Huh?
Even if you get it wrong, you get 1 point for units.
You get minus 1 point for units. If you leave them off, don't leave them off. All right, second transfer would be, oops. Again to the x-axis of 2, right? So we need inertia of 2, which was 348 plus area. I'm just gonna do 1 and then I'll multiply the whole thing times 2 because there'll be 2 of them, right? Yeah. Area is 11.8. And then the transfer distance of 2 is 428. 687, don't forget to square that. And the whole thing is multiplied by 2. So for one of them, I get 563. Multiplied by 2. I get 1126. Oh, 3, 4. Is that a good number? Yeah. Now they're all at this XX axis. We can add them up. So you add the first one and the second one. 1503.93. Inches to the 4th. What day is this? Wednesday. Wednesday of the last week of the term. Questions?
And if it was now geometrical center, then you have to.
Find it. Is that what you mean? Mean like on the plate?
Yeah, you just have to like find X bar then.
Yeah.
And then once you do that.
So just the same thing we did here is you place it. You have to find out where it is. If you don't know, like if it's not a, you're talking about if it's not a structural steel shape. If you can't look it up,
Yeah.
like the plate, you can't look that up and then you have to just calculate it. So if I give you some, I'm not going to, but if I give you some strange shape, right, that you can't look up, like some kind of half circle, right? You can't look it up in the table, but you can look it up in the back of the book and find where that geometric center is. Right?
Because we didn't even
But-
use the 0.7. So.
Not yet. Not yet. We're not done. Right? The 0.77 is going to come to play if we had to locate this. So we made the assumption this is symmetrical. The y-axis is through the symmetry, right? Through the axis of symmetry. If we didn't see that, then we'd have to calculate it. And if you go and calculate this, you're going to find out that it's here. Okay, but you would use this to calculate it because you would need x of 2, x2,
Yeah.
right? And x of 1 is right here. And then you'd have to transfer all this to here. This would get transferred to here. This would get transferred to here. You have to do it because the inertia is going to need that. Right? They wanted both? Yeah. So you would have to do the inertia equation here. The transfer. You don't have to find out where it is because you know where it is, but you got to find x2. Figure that out and then go through this process down here of transferring this to here. Do we have to transfer the plate? No, the plate's already there, but we have to calculate it. Right? So now let's do the inertia of about the y-axis. How will I do this? I'll fold it. I'll just put the feet on. All right, so we don't have to calculate X bar. We know where it's at. Right? Did they give us? They give us the location, 8 inches. So can we look up the inertia about the y-axis for this thing? We looked up the x, 348. Do they give us the y of this? Yeah, they do. So what is the inertia about the y for the C shape or shape number 2?
9.17.
9.17?
Yeah.
Okay. So that's for our C shape. And that's here at this 0.77, right? How do we get the inertia about the y-axis for the plate? Calculate it. It's again, base height cubed over 12. That's the way I do it. They actually give you 2 formulas. But then I just position myself like this, right? The base is gonna be this, the height's gonna be, because it's now in the, where it was in the weak position before, now it's in the strong position. Right? So you just have to remember to cube the right dimension. So this is gonna be 1 and 27. Because it's flipped, right? When we're doing inertia about the y, this is in the strong position, this is in the weak position. So the inertia went way down for the C shape, down from 348 to 9.7. And the plate went way up. 27 is getting cubed instead of the 1. What is that number? 1640.25. 1640.25 inches to the fourth. So we have both inertias. We still have both areas. The areas didn't change, right? Now we can transfer. The plate does not need transferred. It's already at the y-axis. These need transfer, and this is our transfer distance.
Does the 8 go to the 8?
I believe the 8 goes to here.
Yeah.
Yeah. Yep, goes to the shoulder. So the transfer distance is 8.778. So to transfer the C shapes, that was shape number 2 to the x-axis. We need its inertia. 9 point. Oh, yep, thank you. .71 or 17 plus the area, which was 11.8. And the transfer distance of 8.778 squared, and there is 2 of them. Both transfer distances are the same shape, we can just multiply by 2. Say again,
918.3987.
is that already times 2?
No.
Okay, so times 2, since I wrote that.
1836.
1836 inches,
790.
0.790. So that is 2 C shapes transferred, and we need to add to it our plate, our shape number 1. For our total. 3477. I about the y total 3477.04 inches to the fourth
What would you do? Just
added, right? This to the plate.
Oh.
Right, because now they're both here at the y-axis. So this was the C shape. Shapes. This is the plate. So 3477, the other one was 1503. Right? The first inertia about the XX 1503. YY 3477, this thing is way stronger. If a load came in from that direction. Way stronger than if a load came in from that direction. But both are pretty good, so that's really good, and 1500 is not bad. So when your bi-axis, two-axis inertia is pretty good in both directions, then its ability to resist twist is also very good. So any kind of box section, and this is a little boxy. Put that plate also on the bottom and you'd have a heck for strong structure. Good. Good, good. Questions? We got it? Piece of cake. Should be the first problem you work on Monday. Right? Because it's your current knowledge. You shouldn't have to study this. You just did a week of it kind of thing. Both centroids and inertia should be pretty current. So don't spend a lot of time studying that. Go back and look at chapter 3, resultants. Like what the hell were those? Reactions, what were those? Right?
is this problem I use here? Is
It's
it-
gonna be the most straightforward problem out of each chapter. There's gotta be something on the test for you to kind of noodle on though. Demonstrate your problem solving ability. So I'll give you something to chew on in there somewhere.
The extra credit problem.
The extra credit code.
Yeah, that one. Forgot about that one. You want to build that one for me and send it to me?
I would love to.
Okay. Let's do that.
Give us the-
Devin's gonna create the extra credit problem.
Yeah.
He's,
Find the perimeter.
There you go.
The dimensions are listed.
find the wetted perimeter. Fluid mechanics. All right, 14. 14 is like the one we did. We did one just like this, didn't we? In class. Kind of. Is this both axis or just X? Just X. Piece of cake. So we have this one up here. This one down here, and then I'm guessing the composite is somewhere in between. Like in here somewhere. So we gotta find, oops, we gotta find that first. Right? We call that Y bar. I have given you a problem before that's fully worked on the final. Fully worked, and it says find the mistakes.
No.
Yeah,
Terrible.
it's a hard, those are hard, even if it's a simple problem. So you can look forward to that. No, I don't do rounding. I do like, you screw up a rotation of a moment, summing the moments. The mistakes in there somewhere. I did that once,
The 1 and 2.
kinda. It's a nice problem. You don't have to work it, right? It's all worked out for you.
Is it only one mistake or is there multiple?
There's one mistake, but then if that mistake's early, you know, it flows. And usually you have to,
should probably do the problem.
usually, yeah, you have to fix it.
It's better than not look at your
So
problem,
it's
do the
better
problem
just to
first.
work the problem. Don't look at my work. Cause it's pretty hard to see a mistake when you look at somebody else's work. Like you just kind of go along believing everything, right? So it's good to work the problem. Anyway, that's a hot tip. Hot tip. Whew. All right, how do we get Y bar? So it does say rough dimensions, right? So this is 2 and 12. We don't reduce it. So it's not 11.5, it's not 1.5.
So that's what we need to look for.
Yeah, yeah. It'll be always, like, if it's rough numbers, they'll call it out as rough, or they'll call it out as a nominal. Nominal means that's the real number, so. All right, Y bar equals, I'll call this area 1, call this area 2. So area 1, 2 by 12 is 24. Yeah. Did I draw the picture right? Yeah. I did. 4 and 4 is 8 and 12. Yeah. Okay. And then what's the Y distance to number 1? That's this. Y1. Right? Yeah, 13. Thanks. And then we have number 2, which is also a 2 by 12. So its area is 24. Its Y distance is 6, and there's 2 of them. And then there is 24, and then 24, and there's 2 of those. Right? 1, 2 area 2s. What's my Y bar distance? I'm gonna guess at 9. Wrong. Damn. What's the number? 8 what? 8.33. Maybe we'll have that kind of problem on the final. Guess at the location of the center.
Oh my God,
What?
it's always calculated.
How many of you actually calculate? Not guess.
I will calculate a guess and erase my
Yep,
work.
like I'll never see that. Just put your work on a different piece of paper. All right,
Right.
now we know Y bar. What's next? Inertias of each one. Yep. How do we get that?
Based on.
Yep, so I need I of 1 about its origin, and I'm gonna use base height cubed over 12. Base is 12 for number 1, this one. Height is 2. Eight. I could have done that one in my head. Actually, the second one is the same thing, just reversed, where the base is 2, the height is 12. $88. There is 2 of those. We'll deal with that when we transfer, right? Right.
Did not.
Oh, it's like, I read it. Right here and that stuff. Right.
So now we gotta transfer this first shape. Do we have to transfer the first shape?
Oh, yeah.
Yeah, it's not here. Here's our X axis. And here's the axis for the first shape. So it's gotta be transferred that far, D1. We know Y1 is 13. We know Y bar is 8.33. And do the subtraction. Four, six, seven. So we take the inertia, 8 inches to the fourth, and we add to it the area, 24, and the transfer distance of. Went off. 4 point, oh, is it dead? Oh, my calculator died. Charge your calculators before Monday. That's a good idea. What's my transfer distance here? 4.67 squared. All right. Gonna rely on you all for numbers.
Uh-oh.
I know. It's problematic.
I don't think that's a good idea. You don't trust yourself? I don't.
Uh-oh. All right, what do we get for this inertia?
530.67.
531.67?
No, 530.
Somebody else said 531.67.
Oh,
A lot of people getting 531.67. Uh-oh,
Do it
the
again.
firm is failing.
Uh-oh.
Uh-oh. I like 531.67 inches to the fourth.
It's because you just did 4.66, I think.
Yeah, if this is rounded, then we're gonna get some variance.
My
But
bad.
it's still be.
Uh-oh.
Uh-oh, spaghetti.
All right, now we're transferring the second one. Area that's, or the inertia of the second one is 288. And we're gonna add to it area, which is 24, I'm just doing one of them, then I'll multiply by 2. And then the transfer distance. That's gonna be here, yeah? D2. Now, it looks like D2 is gonna be 8.33 minus 6, 2.33 squared. And let's multiply by 2, because there's 2 of them.
6.59.
Is that times 2? 836. Point what?
587.
5872 inches to the fourth. We have confirmation on that from the firm. I got some shoulder shrugs. We're all relying on Devin here.
That's safe, that's fine.
Yeah. That's what I'm thinking.
And the highest grade.
Absolutely.
Okay, bro.
I keep thinking you got like translation. You're translating me as I talk.
Wait.
It's like the United Nations, you know, they're all plugged in. Because they're all trying to.
I got people who didn't register for the class.
I need confirmation on the 836.
It's right.
Okay,
For
Devin,
2 of them.
nice job. Yeah, now what do we do?
Add.
Add them up. We have them all at the XX axis, so 531 and the 836. To get the total inertia, IXX equals. Sure. 8 plus 5 is.
The value definitely great.
13. Okay, that we're doing well here.
Got 1368.
Sure.
Yeah.
I got 1367.99.
And you didn't round anywhere? Or you did?
I didn't round it. Got 13.
Okay. We're good. In strength of materials, we'll be working with factors of safety of probably 3 and up. So rounding is okay, actually. So we're gonna be able to say like 1368 would be fine to use as your design parameter. Because in the end, if we're not within like a factor of safety of 3, we're gonna toss it and start over anyway, so. Rounding becomes less important as we go through the numbers and strengths because we're gonna always be adding this factor of safety. Very good. Wow.
Question on that. What did it be for number 2?
Here,
Yeah, that one.
the 233, D2 is here. So this is my second shape. Right, and it's 6 inches up to that. Yeah, and it's 833 up to that. So it'd be 833 minus the 6. 233.
Sure.
That's what you want to do is get your questions answered. One is moving to the front of the room.
Sure.
I thought you might be presenting something. No. What? John,
I also calculated IYY even though I didn't ask and I get extra credit.
you know what? We knew you were gonna ask for that. And you do get extra great credit. Really good credit.
While we're at it, can I
Your
just?
credit score
add
goes
some
up.
extra credit?
Yeah, sure. That is the last topic in this class, you know. Inertia is the last topic. I mean, we could start into stress.
I don't want to stress about it yet.
Come on. Stress is, managing stress is the key to life, just so you know. So the next course you take from me is actually the key to life.
Oh, man.
Isn't that crazy?
I thought that was the key of life.
Yeah, you thought you already had that
Yeah.
when you got engaged. All right, let's do that. All right. So a great study tool. I do like this book for certain reasons. That's one of the reasons why I like this book. At the end of every chapter has a chapter summary. So what you should do is go to that chapter summary at the end of every chapter and go, okay. Statics deals with forces, you know, here's section 1 just telling me about statics. Okay, I got that. Right triangle trig. If you got it, check it off. Don't spend time on it if you got it. If you need to refresh your right triangle trigonometry, then that's a great study technique, right? I think in chapter 1 we probably have. Right? Units, pretty simple stuff. Really trigonometry is the only thing in there. Law signs, law cosine. I wouldn't bring in your like stack of homework sets. I mean, you can have those available, but that's not a great strategy. You spend a lot of time looking for a problem that looks just like that problem, and it's not just like that problem. So I think a better strategy is to organize information that you know you want to keep straight. Like right triangle trig, sine, cosine, and tangent, maybe. Organize that on a piece of paper, or crib sheet, a note sheet, right? Non-right triangle trig, organize that, cosine law, sine law, how to run it, whatever you need there, right? Then you have this information that's collected kind of in one spot. You're not like searching through the book to find stuff. If you're going to use the book as a resource, you should tab it, like put some tabs on certain things so you can go straight to it. So you're not, again, wasting time thumbing through stuff. It's, I will say, somewhat time sensitive. You should keep track of your time on the test. You got 2 hours, you got 8 problems or 9, haven't decided. It's a moving target, right? But that gives you about 15 minutes per problem, right? 4 problems per hour type of thing. You know, at the 1 hour mark, you should stop and go, oh, I've got 5 problems done, take a breath, right? Or, oh, I've got 1 problem done and it's been an hour, I definitely need to move on Because you know I give partial credit. So you gotta have work on every problem. Don't leave something blank. It's no bueno. Yeah. All right, let's go to chapter 2. Summary by section. Oh, we have more summary than chapter 1. So it starts to talk about forces. It starts to talk about like the definition of a force. I slide that sometimes into a problem. And like, I might have you calculate a force of some kind, and then I'm gonna note that it needs to have all 4 characteristics. What are the 4 characteristics of a force? You're just reading it.
Yeah, it's right there. It needs to
I
be-
know, well,
Oh,
what is it? In not book terms. What's the magnitude? How do we represent that with a force?
That's
It's the length of the line. It's the length of the arrow, the vector, right? What is the sense?
Where the arrow is.
It's the arrow, the arrowhead. The sense is whether it's like pointing that way or pointing that way. What's the direction? The angle. So remember, the angle is a line of action. It's a long, the direction is a very long thing, and we don't know which way it's going in that direction. Right? So the arrowhead gives us the sense, the direction. And then what's the last one? Yeah, where it's applied. Point of application. Excellent. Principle of transmissibility. What's that?
Force can be applied anywhere on the site.
Anywhere along its line of action, right? So anywhere along its line of action or anywhere along its direction, that vector can be applied. Perfect. And then we did, I think, did we do components in this chapter? Yeah, components, that's this. So you could have a problem that says, find the components of a force, just, that's it. But it could be a complicated problem. Like there could be 8 forces, right? Because I might use a problem over and over and over on the test. One of the questions might say, find the components of the 10 Newton force. That's all you gotta do, find the components. What am I looking for when I say find the components? What are the things I wanna know? X and Y components, yep. What else? Important thing. We know the X and Y, if they're rectangular components, they're horizontal and vertical, right? Direction, which way it goes. Is it negative, positive? What is it, right? So don't forget that. Do we want to practice components?
Which one is that? Oh, never mind.
Components? You want to find components of a force? Trigonometry?
Yeah.
Yeah. I heard it, yeah. Let's do let's just rock a component.
You should get
You're salivating if you see a problem like this. You're so happy. For e to the 6 newtons at 17 degrees. Find the components of a force. Find the components of the 4 to the E6 newtons. So it would say find the rectangular. Right?
Or can we do the test in radians?
You can. Actually, you have the freedom to do whatever you want on that darn test.
That's not what it's.
And I'll grade it appropriately. I think it still works.
Is there a reason they don't use radians, or is it just like tradition? They use degrees, I guess.
Don't know the answer to that one. Yeah, don't know that history. That's a good Tom McCormick question.
Class that you might have needed strength for.
Oh,
That people were. asking.
structures?
Yeah.
I did. Did I get a reply? I don't think so. Tom's not really good at email. No, you confirm that.
Man, Blackshire, where the students is.
Oh, I have no calculator. So sad. What do we get for the X component? I'm hearing. I'm hearing different numbers.
3.825 E6. 3,800,000.
3,825. Is it 3 point?
Yeah, 3.
Thank you. 3 point e to the 6 newtons. Positive or negative?
Negative.
It's negative or pointing in that direction, because we don't really work with negative forces. We just work with forces in a negative direction. So to collect these effects, we use a negative symbol. Good. Sine 17 is going to be y over the hypotenuse 4 e to the 6 newtons. What is my y component?
1.1696.
1.169 e to the 6 newtons down negative. On the test, it'll have a little note at the top that says all numbers are precise to 2 decimal places. So then you'll report all numbers back to 2 decimal places.
You're technical for E6. Is it 4 times 10 to the 6th?
Yep. Yeah, if you're, so most calculators will have an E button. So mine does. I can't show it to you because the calculator's dead. But the way it works is I just type in the EEX button, and then I can put 6 in, and it writes in 4E6. And then when I hit enter, it puts it out to 4 million. So,
The most calculator also has either E or the time 10.
Yeah,
to the power.
yep, that'll have a times 10. So look for that button, it's helpful. Excellent.
I know.
That's chapter 2. I don't think we did anything else.
I wish we still did this.
So we're in such harmony right now. So we're in a happy place.
What chapter was the midterm up to? Was that 4 hours?
I think we did chapter 4 through equilibrium.
I was just looking at that right now. It goes up to.
I don't remember. Chapter 3 was big. Big. Chapter summary is here. We did moments. Calculate the moment of a force. And we talked about Vergenon's theorem. Vergenon. So I won't ask you questions like that, like what's there, because you can just look it up, right? I don't need to ask you that kind of question. But the concept of this theorem is, anybody remember what that is?
Yeah.
It's, you can read it, I get it. But what does it mean?
You can split it. The components.
Yep, that's right. So it means that I can use this number to calculate a moment about this point. Right? I can use this vector here to calculate a moment about point A. I would take the vector times the perpendicular distance to get that moment. Right? I could do that. If I could find this distance, I could take 4e⁶ times that distance right there, the perpendicular distance, to get the moment. Or I could use its components, which are actually here, y and x, and calculate a moment for that one, and calculate a moment for that one, and get the moment. You can do it either way. That's what Vergenon says. Says, hey, you can use the vector times the distance to get the moment, or you can use the vector's components to get the moment. And there's times where the components is a lot easier than using the original vector because of the given distances in the problem. So that's all Vergenon says. So components are exactly the same effect as the original force. Nothing changes when you put the components in and take the e⁴ away. The effect's exactly the same. The effects are broke up into x and y. It's a little easier to deal with often. All right, cool. So couples, we never talked about couples, just so you know. So if you see couples in here like, oh, what the hell's a couple? I never talked about it. It's not necessary to go into couples at this point. We kind of circle back in strengths to rediscuss them and understand. You're doing it, you're using this concept of couples when we collect forces at one spot, which maybe you remember and maybe you don't, but when we do resultants, we have to collect forces at one spot and then distribute that back out. The way we can get away with doing that is called a couple. So don't stress out that you don't know what a couple is, because you kind of do. You're using it when you do resultants. And I think, did we do resultants? Yeah. We started into resultants of parallel systems. So it says resultants of parallel force systems. We should practice that. What do you think? Remember that? Anyone remember that? Given a parallel system, find the resultant. It's got a wire up here pulling on it at 300 pounds at 40 feet. And then it's got a wind load pushing on it at 4,000 pounds. Point A, 40 feet to the top. And this is going to be, I don't know, 30 feet. I was making it up. And I already concentrated the wind load for you. And the question says, what's the result? And it says, oh, it's actually goes into the ground, right? It's buried. There's concrete. Get enough on there so you're distracted from the real problem. Birds flying. Planes flying. Not a bad point. Yeah. It's like a, what's that called? The cloud, Tracer.
300 pounds?
300. Yeah, so the problem I'd say, find the resultant and where it is located on the pole. Find R resultant. And where what do I do first?
Some.
Okay,
Yeah, versus Y forces.
yep,
Moment about.
everyone like that idea? Some forces in the X. So remember, you're gonna collect them at a location, right? So when you're doing resultants, no free body diagram. Don't put in reactions, right? Nobody said free body diagram, that was good. Nobody said that. In other words, we're not gonna remove all this support and put in a bunch of reactions down here. That's not what the question's asking. We just wanna know the resultant of the given forces, those two. So you should think about where you're gonna collect them. Add them there, right? Since we wanna know, from A, we might wanna move them to A and then redistribute it back out. But he's right. We need to sum the forces up to get the total translational effect. Plus 300 minus 4,000 equals R. Minus 3,700. So that is R. That's the resultant. Yes, sir. Oh, dang, Kevin, back here.
In the back. Oh, okay.
Yeah.
That was great. See what Ryan does.
I know, that'll be taking you right out.
Oh. That means it's too much math. So
Too much math, they need no final.
I know exactly.
That happened in everything.
Math knows.
We all, it's a yogurt bowl with protein.
Okay, who doesn't drink coffee?
Dancing? I take caffeine
Yeah,
straight.
here's my son, so bad.
Wait, no, 17.
Okay, because I was trying to drink
Yeah.
coffee
No. Bro, you wanna sign passport?
for everybody.
I'm with it right now.
So there are four.
Okay, I like coffee, I just don't drink it.
I thought you were like.
I don't like the black coffee.
No, bro, what did you say? Hey, bro's are gonna be very. 27. Bro, got away. I would do it.
You look like you're 19.
Try, bro.
Next time.
All right, so now we have this. Right, so that essentially we move everything down to point A, but we have to bring the moments with it. So you're gonna have to do moments about whatever point you move them to, right? I moved them to A is what I'm telling myself. So that means we've got to sum the moment down there and get the total rotational effect. So moment of the 300 is what? 300 times 40, rotation.
Negative.
It's either positive or negative, I agree.
It's
Which
negative.
one?
It's
It's negative. Clockwise. And then 4,000 times 30. Rotation, positive. That is gonna equal the moment at A. So it doesn't equal 0. We're not, that's equilibrium. We're not there. We're doing resultants. It equals the moment at A. So what is the moment at A? So I have no calculator. I can't tell you.
108,000.
108? And the units?
Pounds.
Oh, yeah.
Foot pounds. And it came out positive? Yeah, so that means the moment a day is here. Doing that. Right? It's counterclockwise effect, this rotational effect. So now down here at A, we have 3,700 pointing this way. Pounds. And a moment a day. So when you collect forces at one spot, you're gonna end up with a force moment at that location. How do I know where this actually is up on the pole? And potentially off the pole, because it's the effect, it can be off the pole, so. Since I made this so big, I'm guessing it'll be off. Yep, so we know moment equals force times distance. To get the distance, we take the moment and divide by the force. How much?
29.189.
Feet. That's where it's at. Up here, just under the 30, right here. Is where the resultant is. Find the resultant.
So it wasn't off.
Was not off the pole. I guessed wrong.
I did like,
Trial and error.
I did like the 108,000 divided by the 37.
Yep. Yep. Parallel's the easiest one. When you get angled forces, it becomes a little more complicated.
That's right up in the air. Or
There-
the left. Or
Is it right, left, up, down? What is it?
I think it's-
Where would it be? From point A? Up.
Oh, right.
It's literally vertically up from point A. Right? And that's why I gave you a vertical problem, because we didn't do as many as the horizontal problems. Horizontal would be left and right of the point. Vertical would be up or down from. Then we'll do one more concept.
Moving up to this one.
Yeah,
So our moment on this one was 1,000, oh, sorry, 108,000.
correct.
And the force is, in this case, would be the resultant, right?
3,700, yep.
Minus 37.
Yeah, in a negative direction.
So when you do the division, the actual distance would be minus.
If you put the negative in, but remember, the resultant has to make this effect, the moment effect. So you know whether it which way it goes based on the rotation of the moment, not on the sign. Right? So you have to put that force up here to make that kind of rotation, which is the same. We want to make the same rotation. Yeah. So I don't put in a negative or positive here.
Okay.
I just do the number and then think about like, which way does this thing gotta go? Because I have to make that moment. That effect. So if you have a horizontal problem and you end up with this and this, right? Your resultant is this, and then your moment is this. Where's the force gotta go? To the right or to the left?
Right, to the right.
Gotta go to the right because it has to make that moment. If I collect it in the middle, right? And then this is the moment I end up with, which way is it gotta go? It's gotta go left. Yep, you gotta make that effect. Good. So the other one we did with the resultants were these. What kind of force is that? Concurrent, everything going through one spot. Yeah. And how do we find the resultant of that? Add them all together, what's the easiest way to do that? Components. If there's only two, how could you do it?
Parallelogram.
Yep,
Couldn't you do that with the force system above, just like
You
one
don't-
and then?
yeah, you could, I don't advocate it and I definitely don't show it, because we don't need to complicate things, but he's saying. We could take these two, add them together. Correct? And get that, and then take this one and this one. This is even hard for me to draw, like that, and get this, R. Right, do it twice, parallelogram twice, or 3 times or 4 times,
I did not, when we had
No.
the, like,
you do it then.
no, when we did the, when we had like the 8 vectors.
Yeah,
I did it components, and then to check my work, I did it parallelogram law.
nice. So yeah, this, you can just literally do a triangle, right?
Yep.
Add them together tip to tail, and then that becomes R. So if there's 2 vectors, you can add them tip to tail, and you'll get R, and you can solve that triangle. But if there's 3 or more, components is the way to go. Collect all the X's, add them up, collect all the Y's, add them up. RX, RY, you can get R. So there you go. We are through chapter 3. So on Friday, we'll do 4, 5, and 6. Right? 7 and 8 we just did. So we can if you want, but I don't know if you need centroids and inertia. I think you got it. But we can. We can. Take one look at my home. All right, we're done.